let's find out the integral from 0 to 1 of x to the power of b minus x to the power of a over natural log of x dx. We're going to quickly just recall those two simple facts to help us solve this integral. First of all, let me show that x to the power of u equals e to the power of u times log of x. So if we let x to the power of u equal to e to the power of y, and we'll find out why. So take the natural logarithm of both sides. We have natural log of x to the power of u equals natural logarithm of e to the power of y. Then just take u down to front. U times logarithm of a. X equals to y times log of e. Then that is simply log of e is equal to 1. So that's y. So y equals u times natural logarithm of x. So that means, so x to the power of u can really be written as e to the power of u times natural logarithm of x. So that's called the changing base formula, right? We change the base into the base of natural logarithm. Given any base at all, we can always do that. So let's prove this fact. So knowing that the so here from a to b, x to the power of u du, so x to the power of u du can now be written as the integral from a to b. So x to the power of u can be written as e to the power of u times log of x. So e to the power of u times log of x du. Notice that here we treat x as a constant, right? Log of x is a constant, and integrating with respect to u. Now, we already know that e to the power of anything, the antiderivative should be e to the power of the same thing times some constant, which we will figure out. So that is equal to e to the power of u times log of x times some constant. Now, if we now differentiate this term, we will have this expression itself times, using chain rule, times, remember, u is the variable and log of x is the constant, right? So just simply times the constant, that is log of x. But we're hoping to reach to this expression, this integrand. Therefore, we should simply divide by log of x, just so cancel out the log x, right? So divide by log x. So this is indeed its antiderivative. Okay, so then again we replace the top with this thing, right? Those things are the same, x to the power of u. So x to the power of u log x. Remember, here we just say lower bound a, upper bound b. So x to the power of u, so lower bound a, upper bound b. Still remember, u is our variable, right? So after we replace u with b, u with a, and take the difference, we have log x remains the same. Top we have x to the power of b minus x to the power of a. Right here, x is a constant here. So we've proven this fact. Now, here, so we can now see that the integrand can now be written as a definite integral as well. So now we kind of have a definite integral inside of a definite integral. Now, this original integral can be written as integral from 0 to 1. The integrand now becomes this. So bracket integral from a to b, x to the power of u du, okay, bracket then dx, right? So meaning, first of all, we integrate the inside with respect to u. Then we with integrate with respect to x. Notice here that this inside integral is will actually turn out to be a function of x. Why? Because remember, we integrate with respect to u first. Then we just replace after we get some expression afterwards, we just replace u with a and b. Therefore, whatever there is u already will become a or b. Therefore, we just get an expression that involves only x and ab. Now we treat ab as constant and treat x as a variable and integrate with respect to x. So this makes perfect sense. Now we can switch the order of integrals, right? So equal to first we write so integral from a to b, and bracket integral from 0 to 1, and copy down the same expression x to the power of u. We say du here, we say dx first, then bracket, then we just say du, right? So this time we just integrate with respect to x first. Then we come up with an expression that only involves u and some other constant, and then we integrate with respect to u. Now, it is actually safe to interchange the order of integrals simply because the double variable function f of x and u, right, being the double variable, is actually continuous over the rectangle of because remember the x is bounded by what? X is bounded by 0 and 1, and u is bounded by a and b. So imagine there's a rectangle, right? So the width, length, 0 to 1, a to b kind of rectangle. The double variable function is actually continuous on that rectangle. So it is actually switchable, right? Legitimate. So therefore, we just simply say that is equal to integrate inside first, right? Should be easy to integrate. So a, b. So using the normal rule of antiderivative, so treating x as a variable, u as a constant, right? Since now u is a constant, this easily becomes u plus 1, x to the power of u plus 1. Then lower bound 0, upper bound 1, then we just du. Now, right, so u plus 1, if we just double check, differentiate with respect to x, so u plus 1 times bottom u plus cancel out, then x to the power of u plus x to the power of u minus 1, x to the power of u, yes. So this indeed it's antiderivative, right? Now we just replace x with 1, x with 0, take the difference. Equals integrate from a to b. So x becomes replaced with 1, so 1 to the power of u plus, so 1 over u plus 1. X becomes 1, becomes 0, so 0, 0 over, so that's 0. So in the end we have 1 over u plus 1. 1 over u plus 1 du. So this is easily log of u plus 1. Lower bound a, upper bound b, and that is easily replace u with b and replace u with a, take their difference. And using the logarithm rule, we have logarithm of b plus 1 over a plus 1. So this should be our final result.